So, hey everyone, I'm Daniel Cardozo. I'm a software engineer at Whiterabbit.ai. I also want to say I appreciate all of you being here. I think you're going to get something out of this talk, whether it's about the AI, the impact, or how we use the Hashistack under the hood. So today, I want to tell you about real-time radiology, or RTR for short. It's this a system we've built on top of the Hashistack that uses artificial intelligence to detect breast cancer in real time. So first, I'll give you a bit of a background on who Whiterabbit.ai is, what it is we do, and what our core mission is. Then we'll do a deep dive on the underlying infrastructure, what we use Terraform and Packer to provision and help us develop RTR. And at the end, I'll describe some of the lessons we learned using the Hashistack and building this complex system. So let's get started. So who am I? I've been at Whiterabbit.ai building backend services and infrastructure since October 2018. I've included some of my social media handles here if you want to follow or give a peek to those. And I've also included a picture of an actual white rabbit to dispel any confusion about what our logo actually is. And on the right, that's me, but let's get started. So if you want to provide any feedback or ask any questions, you can either scan the QR code or go to the link, and it'll be redirected to a Google form. I will also be presenting these at the end of the talk in case you have any questions or feedback you'd like to give them. So now let's start. So Whiterabbit started as a company in the San Francisco Bay Area in 2017. Since then, we've grown to over 100 employees, 35 of which are on the software engineering and technical staff. So this includes data engineers that are responsible for building and massaging our data sets, the machine learning team that builds the AI models we use and run in production, as well as a series of full stack and DevOps developers that help us build the software ecosystem on top of the AI. And as well, we actually own 9 radiology clinics, one of which is in California, 8 of which are in Phoenix, Arizona. So it gives us a bit of a variety in who we actually employ, what kind of minds we get when we're trying to attack some of these hard problems. And we're also a very distributed team. We are mainly located in the US, mainly California, Nevada, and Arizona, but we also have a sister engineering office in Mumbai, India. So what is it that we're trying to do and accomplish? Our mission statement, clear and simple, is to eliminate suffering through early detection. If you can detect disease and ailments much faster than before, perhaps much faster than a human, you significantly increase the positive probabilities and outcomes for your patients, or customers as we like to refer to them. Specifically, we're focusing on breast cancer. There are a variety of ailments that are ripe for attack by AI and new technology, but there's a lot of data on breast cancer. There's a lot of thinking and research going on in that field. So that's what we decided to attack first. And the way we do that is by building AI models to detect breast cancer and introduce them to the clinics by augmenting typical clinical workflows. So some people might be worried that AI and other technology will displace humans in the medical field. But what we're trying to do is integrate them so humans can use them, be more productive, whether that's our radiologists, our clinic technicians that are also in those 9 radiology clinics, as well as the patient. The patient experience is what we're trying to optimize the most for. And as we'll soon see, real-time radiology disrupts or affects their experience in ways that hadn't been done before. But before I can talk more about real-time radiology and what it is we do, there's some background knowledge that's necessary and a prerequisite for talking about these topics. So radiology, which is what the talk is on, is the medical subfield that uses medical imaging to diagnose and treat medical ailments. So if you've ever had an X-ray, an MRI, a CT scan, all of those are grouped underneath the radiology specialty. And what we'll be talking about today specifically are mammograms, which are an X-ray of breast tissue. Artificial intelligence, big buzzword. You may be familiar or have heard of deep learning, machine learning, classical models. At its core, you're just trying to teach a machine to emulate some human behavior or function that previously machines couldn't do. So whether that's identifying objects or classifying things in a given image, or if you're trying to determine whether a piece of text is semantically positive or negative, AI can be used in both of those scenarios. And breast cancer is when cancerous tissue is formed in the breast. A lot of you may know about that. So here's some example images I wanted to show just to give you a glimpse into what the radiologists, what the doctors will actually see when diagnosing patients. So on the left, you have an X-ray of a right hand, but more interesting, on the right, you have an actual mammogram, So these are what radiologists look at when trying to diagnose and look for benign or malignant masses in breast tissue. And not only do radiologists look at these images, but the AI models we train also receive them as input. So we could talk about AI all day and a lot of the interesting work there. But to summarize some of the work we've done, we have a data set from a top 5 US medical university. And this data set has close to 2 million images. All of these are mammogram or tomosynthesis images. So mammogram you can think of as a 2D X-ray of a breast. A tomo, or tomosynthesis image, is a 3D representation of a breast. So it's much more granular, provides a lot more information to the radiologist. And the algorithms, or the way we actually build these models, are using supervised learning. So I've included a nice diagram of that. Those of you familiar with Silicon Valley, the TV show, may already be familiar with this. But the way it works is it's a machine learning task where you train a model to learn a function by providing a lot of example inputs and outputs. So for this model, we're training it to learn whether or not an image is a hot dog. The inputs and outputs that you provide as examples will be images as well as a label, which is whether or not they're a hot dog. And via the training stage, your model will become more accurate, more precise, and will learn the function over time. Usually and typically, the more data you have, the better your model will be. And once those models are built, we use them to run inference in our clinics. And inference is when they receive new inputs that they've never seen before. And using the results they give us, that is how we do the core work of real-time radiology. So here's an example image of how AI can maybe apply to the mammogram we had seen earlier. So this is an image taken from an MIT study that indicates how an AI can identify a cancerous growth in a breast, perhaps earlier than even a human radiologist can. So our models do the exact same thing. Given an image, they can give you a probability of where the cancer could be, as well as whether or not there is cancer, or the mass is malignant. So using some of these cool determinations, you can build software, an entire ecosystem on top of them, to actually get that knowledge back to the patient, get it back to the clinics, where they can be integrated effectively. So now we kind of have some of the problem context in our mind. Now let's talk about the underlying motivations. So one of the key ones is we want to reduce the time it takes from the screening to the diagnostic stage for a patient. So typically this is 30 days, and when you are going to be checked for breast cancer, typically you will go for either an annual or biannual mammogram. And this starts off as a screening phase, which is an initial test. It's one of the less invasive images they can generate. And from that, from the results of that, you will either proceed to the diagnostic phase, which is secondary tests that will tell you more information and will help the radiologist actually make a determination about whether or not there is cancer. And so typically, the average in the United States, this will vary based on country, is close to 30 days. However, in real-time radiology and the real-time nature of it, we can sometimes bring this entire step down to a single day, but typically only a few. And so by detecting things earlier and getting these scans done earlier, our patients get results faster and they can receive treatment faster as well. Secondarily, going back to our core mission, early detection increases the positive probabilities for our patients. So there's a morbid term in the medical world called the 5-year survival rate. And that is the likelihood a patient diagnosed with a disease will be living in 5 years. So if the cancer, breast cancer, stays in the breast, those outcomes are quite high, 99%. However, if they are not detected early and they spread to a foreign part of the body, they can go down to 27%. So if detected early, the outcome is very positive, but only if you detect it early, and tools like real-time radiology help our patients do so. And the way we do that is using these models we build, we can actually triage suspicious cases a lot faster than a typical human radiologist. So I'm going to grab some water, but here is where all of the work is. So the typical patient workflow is you will come in for your annual mammogram, and as you're going through the screening stage, you will have images generated of your breast. These are generated by a modality or a very special camera use some cool physics to get the very granular images you had seen earlier. And using those images as they're generated in real time, as well as their health and patient records we have at the clinic, we feed all of that data into our Whiterabbit triage engine. And this triage engine is responsible for ingestion of images, filtering out images in cases we cannot handle, but also running inference against the images for each patient. And it will output one of two things. One, maybe the patient has a suspicious set of images, and with that information, we will elevate it on the radiologist queue. So radiologists have task queues, very similar to software, called work lists, which are just queues of patient cases with all the associated data they need to actually make a determination. And so by elevating this, if the images are suspicious, onto the top of the radiologist queue, there's potential for the radiologist to see those images right after the patient has generated them, meaning the patient is still in the clinic. And with this information, we can expedite the patient to the diagnostic phase on the same day. So that's the best outcome. Typically, because of scheduling conflicts and other things that can come up, they will be handled in the next few days. But it's a lot faster than the typical 30 days, which is the average in the United States. However, if the image is not suspicious, it will still go to the end of the radiologist queue and will eventually be read by a human. And an important insight here is that a human will always see the records. We are not trying to remove them from the process. We just try to expedite and triage cases as best as possible. And so this has actually been deployed in our clinics in April 2019. And a lot of the immediate feedback we got was quite positive. One of them being the reduced anxiety. So typically, you'll go in for your screening exam, and it may be a month or upwards of a month before you receive the results back, or a call back saying, please come back. So all this time, the patient will be worrying about this. They'll have other responsibilities to worry about too, but by reducing that anxiety via the reduced time, there are much happier outcomes. As well, it helps increase the productivity of our radiologists and our clinical staff because they can handle the cases that need the most help or most work, sometimes on the same day. We save a lot of time in the future. And so this is what real-time radiology is. As of right now, the actual software component might be quite nebulous. What is the Whiterabbit triage engine? And most importantly, what system and infrastructure does this actually lie on top of? And that's when we get into the infrastructure overview. We'll talk a bit about the underlying systems and what is there. So at high level, we have a hybrid cloud, multi-cloud, multi-platform, whatever your preferred term for it is, where we have centralized services on Amazon, but we also have software and hardware we deploy to our clinic sites as well. So you can see there that each of these clinic boxes, or clinics rather, have a box packaged with the microservices that make up real-time radiology that all run in Docker and have an NVIDIA GPU because those are required for running inference at the edge in a much faster way. And so for those of you who have used hybrid clouds, you might be wondering, these are hard to manage, they're hard to orchestrate. Why is this your model? And one of the primary initial constraints is that the medical images that are generated by modalities can be quite big. They can be the hundreds of megabytes, sometimes even gigabytes, and not every clinic we had operated in, especially at the beginning, had fiber or even a direct connection to Amazon. So one of the biggest bottlenecks and constraints was actually transferring these images to the cloud, which is why we went with this hybrid model. And one of the interesting things about hybrid models is how can we achieve deployment of our software in a uniform way across these two environments which run on heterogeneous hardware. And the container orchestrator we use to do that is Docker Swarm. So we've had a lot to talk about Kubernetes, Nomad, and other orchestrators. We went with Swarm for a few reasons. One, it's quite simple. For those of you that have used it, creating a distributed cluster is quite simple. It comes with a lot of interesting benefits like overlay networks and distributed key value store. As a basic architecture, managers and workers, very similar to Kubernetes. It also has node-aware scheduling, which is very similar to all container orchestrators. What this allows us to do is, if we want to run a specific version of RTR at a specific clinic, because the software may be different, or the workflows are just a bit different, we can do that using node-aware scheduling, where we can run a series of containers or microservices on a specific clinic box using node labels. So here's actually one of our boxes that we have deployed. Some may be pedantic and call this a rack, but the premise is the same. These are Linux boxes with an NVIDIA GPU. And each of these boxes actually becomes a member of our distributed swarm cluster that has instances both in the cloud and in the clinic. And so these are the boxes that actually run RTR, other microservices. And these are what we ship out to clinics to actually run the software and do the compute on the edge. So here's a slide describing how we use the cloud, which is basically saying we use it to do most things. It also indicates just how confusing Amazon service logos are. Very unintuitive, very confusing. But we try and use Amazon for as much as we can. We're still a small team, a very small infrastructure team, so we try and lean on their compute, storage, networking resources as much as we can. Whether that's EC2, Lambda and Fargate for various use cases, S3, which is where we actually store all of our medical images for data processing and batch processing down the line. All the networking resources, including a VPN, which I may not have mentioned before, which glues our clinic instances with the cloud. As well as for other infrastructure, whether it's Route 53 and other resources they have. So when you have a hybrid cloud and distributed system, you need efficient monitoring and alerting, especially if you're a small team. You need something to tell you there's a problem so you don't go manually search for one. And so the way we do that is with this stack. We use Elastic Beats. Elastic is the company that does Elasticsearch. And they act as lightweight agents in all the nodes in our swarm cluster. So these will keep track of metrics such as CPU, disk, RAM, network, and pump all of those to Elasticsearch. And they will also gather logs from our containers, our system processes on the boxes, and that'll all get indexed in Elasticsearch. After it goes to Elasticsearch, we use Grafana to visualize all this data, to build high-level dashboards indicating the health of the system as a whole. We also use CloudWatch, because you get it for free by using Amazon, and pump that data to Grafana to get some more dashboards that are built in by default. And our alerting tool of choice is Opsgenie, very similar to PagerDuty, if you have used that. So that's the tool that will actually alert you that a problem has happened, which is what happened to me last night, my coworker, when we arrived in Amsterdam. So now it's, how do we actually manage this infrastructure? There's a lot going on. It may be surprised to hear that there are only 2 engineers building this part-time. So we have very multidisciplinary teams responsible for building the services of RTR, as well as the infrastructure it runs on. So myself and someone else do both of these tasks, as well as ingest all infrastructure requests from other teams, whether it's product, the machine learning team, or even the data engineers. And the only way you can really manage all this complexity with such a small team is to lean heavily on tools, which is where the Hashistack comes in. The 2 tools we lean on the most are Terraform and Packer for managing all of our infrastructure, as well as all the virtual machine images that we build and deploy. I included this in case some people were not too familiar with Terraform, but there have been a lot of great talks, especially the keynote today. So we can go through this slide pretty fast. But we use Terraform to provision all of our infrastructure and resources on Amazon, Docker Swarm, as well as Postgres for RDS instances in the cloud. And Terraform is great, as I'm sure all of you are aware. We use it for its modules. We use it for its interpolation functions. It allows you to do some compute and logic as data flows around your Terraform code base. The current model we use is a very CLI-based one. Being a team of 2, it's very easy to have a model where you'll do a Terraform plan, make a PR with the plan, and then just apply it once the PR is approved or merged. As we think about growing our code base and getting other developers involved in the process, we're thinking about leaning more on Terraform Cloud or Terraform Enterprise in the future. So now we'll get into a few small case studies of how Terraform lets us create some resources or modules that are beneficial for an engineering company in the medical space. So in America, there are federal regulations governing how patient data are handled, and that is HIPAA, which describes, which is Health Insurance Portability and Accountability Act, which describes how data is supposed to be handled in transit, how it's supposed to be secured both physically as well as electronically. So think about it has to be encrypted in transit, encrypted at rest, and all companies you ever partner with to store this data have to be HIPAA compliant. And the term or the resources that HIPAA talks about are PHI, or protected health information. ePHI is just the electronic equivalent of that. And so one of the things we do is, as I mentioned before, we store all of our medical images in S3. And it's very easy to accidentally misconfigure permissions on a bucket. There are bucket policies, IAM roles at play, as well as access blocks, which Amazon added recently. And what we do to prevent ourselves from shooting ourselves in the foot and accidentally exposing this data is by wrapping in a nice, easy-to-digest module right there. So it's a very powerful, like 10, 12 lines of code. And internally, it makes buckets with the strictest permissions possible. A lot of you may have either built a similar module or found an open source one online. And what this allows us to do is allow our developers to make pull requests, adding new buckets for new experiments, new work, without having to worry about the security constraints or concerns under the hood. Our swarm workers, so that's our container orchestrator of choice. It's quite a complex system. Requests come in from either the VPN or the internet, go through one of our load balancers, and then are directed to one of our swarm worker groups. So we create these swarm worker groups, which is where compute is actually run. Our containers are actually run and instantiated. We provision these with different instant types in EC2 autoscaling groups. Not only that, each group may have a different type of task, a different set of labels, whether they're more tuned for long-lived services, building and testing AI models, or for batch jobs or worker pools. So there's a lot of complexity here that if you have to manage it via a script, Puppet Ansible can be quite hard. But the interface we have for doing our work with this is via this very dense Terraform module. So don't expect everyone to understand or read through the entire thing, but it shows how we string modules together, whether we have dependencies on a module, building load balancers, DNS, making EFS instances. All of that is glued together here and is quite understandable from the outside. Internally, it may be a bit complex, but if any developer is curious or wants to instantiate a new group, they have all the tools they need to do so. And Terraform is quite powerful by allowing us to encapsulate all the complexity on the previous slide into this one module. And lastly, the VPN. So this is the glue that brings our hybrid cloud together. And what it does behind the scenes is instantiate AWS virtual private gateways and customer gateways to allow us to integrate with our 9 clinics. And the module interface is quite straightforward. Simply provide the WAN IP or the gateway IP of the clinic, as well as what CEDAR blocks or IPs they want to expose across it, and you're pretty much good to go. We do workflows like this quite often, so having it wrapped in a module makes us doing it the second, third, nth time much easier. So the second tool I had mentioned that we lean on a lot is Packer. We have a lot of instances, and the way we run our software on top of it is always via VM. So we build AMIs for Amazon, QCOW2, or Kimi images for the clinic boxes. And what this allows us to do is bundle a lot of dependencies, startup scripts, Docker, into the VMs that we use everywhere, which is where Packer comes in. But more importantly, and this goes more to what the benefits of VMs are, the software environment is always the same, despite heterogeneous hardware. So the box I had shown on a previous slide, that's one version of the box we deploy to clinics. We also have 2 others with a variety of GPUs and physical resources. So having a tool like Packer allows us to build this homogeneous software environment where you may not know what the underlying hardware is. One of the interesting things we do to minimize some complexity is have a Packer inheritance model, where if you want to build a new model for a specific purpose, whether that's to build an Elasticsearch cluster or a clinic box, we have a set of tooling and scripts that let you do this quite easily. Racker, I believe, is an open source tool that some of you may be familiar with that lets you do something similar. And this is mostly what we use Packer for. It's a very simple tool. Allows us to do some very powerful things. And just for a small dev team, allow us to offload a lot of the complexity to the tool itself. Next, box installation. So you may have questions about how we actually deploy these boxes to our clinics and how the installation process is. Integrating with on-premise environments can be quite difficult, especially if you don't control all points of the process. But our current process is we'll build the Whiterabbit box in-house. We'll deploy it to a server room that's hopefully a lot cleaner than the one in the picture. And then the clinic staff just simply have to plug it in to a redundant power supply, as well as an actual power supply, and just turn it on. And this begins a complex bootstrapping process. When the box comes on, the bare metal box, it will download one of the VM images, the QCOW2 images, from Amazon S3. Each of these boxes are provisioned with a different IAM user and key, allowing it to do this on boot up. Once the image is pulled down, we use libvirt to actually instantiate it. And once the VM image comes up, that begins a separate bootstrapping process. And what this entails is the VM comes up, it will run Docker, and then run a bootstrap script that will have it join our distributed swarm cluster across the VPN. And once it's joined the swarm cluster, some cool, interesting things happen. First of all, our monitoring containers will immediately begin running. Using Swarm, you can do global scheduling, as other container orchestrators allow you to do. What this means is we want every instance part of our swarm to actually run our beats, our lightweight agents that forward metrics to Elasticsearch. They will also immediately begin to pull down the images required for RTR. We'll add a specific label to this clinic, or node rather, saying it's a clinic, and then immediately the Swarm scheduler is smart enough to schedule the RTR containers onto it as well. So it could be a potentially very manual bootstrapping process. With the power of Packer and a lot of automation, can happen in 10 minutes, 20 minutes, mostly dependent on the bandwidth you have available at the clinic. So future work, being at the conference the past 2 days, this has changed quite a bit. There's a lot of cool things that HashiCorp has in store, and a lot of ways and tools that would make our existing architecture actually a lot simpler. Terraform v12 is one of those tools that we're looking forward to using and adopting. We have a lot of custom DSLs and a lot of glue code that can be greatly simplified with its richer types and all the cool fixes they have. Another one is Nomad for container orchestration. We went with Swarm because it was very similar, or rather very simple. But using Nomad is an alternative way. But one of the coolest ways I didn't know making the slide is all the cool console work that's gone on. So I'm talking about the service mesh, the mesh gateways that were presented in the keynote. A lot of that would actually reduce the complexity we currently have with our VPN and hybrid cloud solution. And lastly, Terraform Enterprise or Terraform Cloud. We're trying to grow the DevOps culture at Whiterabbit to offload some of the work to our actual developers. And Enterprise and Cloud let you do that with a nice UI and a much easier interface for people that may not have used Terraform or any of the Hashistack before. There are a lot of lessons learned doing this. First of all, hybrid cloud is hard, especially when you're on a small team. There's a lot of points of failure, whether it's on the VPN end, the cloud, the on-premise resources that you can't easily take down or instantiate, and it could require a lot of manual debugging in case something does go wrong. So this is why you have to really build a powerful monitoring and alerting system so you can deploy and be alerted of any issues as they come up. Secondarily, consistency over correctness. If you instill certain patterns or tools into your organization, it prevents people from drifting off and doing alternative workflows that may not be tested or used as much. On a startup especially, people have their own way of wanting to do things, and they want to iterate fast. But if you enforce some consistency, such as Terraform for how we provision all of our infrastructure, we no longer get into problems or snags where a lone developer who somehow had root access is provisioning their own instances and kind of wreaking havoc on infra. Then we have self-serve DevOps, or help your devs help you. Being a two-person team, you want to offload a lot of the cognitive complexity and manual work to the developers as much as you can. And the way we do that is with friendly Terraform modules, internal learning sessions, so we can disseminate some of the cool stuff the Hashistack allows you to do to developers. And because the tools are quite simple and well made, this process is quite nice. A lot of developers are eager to learn these things, just for both self-learning and to help their actual work. And lastly, making your Terraform modules extensible. Sure, everyone is aware of things like this. You never know when you're going to use it again or how many times it'll be instantiated. So if it's built in a way where you can easily take on new features or resources, that definitely saves you some time in the long run. So closing, Real-time radiology helps patients receive their results faster than ever before. Reducing the amount of time a patient will wait from 30 days to potentially a day allows you to really change the healthcare space and patient expectations in ways that aren't typical, have really been seen before. And Terraform and Packer have allowed our small dev team to really build out this complex infrastructure and actually manage it, both creating and building it, responding to requests from other teams, as well as building some of the actual services that compose RTR. So I want to say thanks for listening. I've had a great time at this conference. I want to say thanks for HashiCorp for putting on such a great event. And as promised, if you have any questions, you can go to this URL or scan the QR code, and you'll be redirected to a Google form to provide any feedback. So that's all I had. Thanks for listening. Hope you got something out of it. If you want to ask any questions in person, feel free to find me at the conference. I'll be here for the rest of the day. But thank you.